Introduce a superheated object to a cold space, and the energy immediately bleeds outward. Thermal energy is physically relentless. In physics, this movement is called thermal energy transfer. The entire process is strictly driven by a temperature gradient, meaning energy flows exclusively from regions of high temperature to regions of low temperature. This flow continues continuously until the system reaches a single, uniform temperature across all areas. That final balanced state is absolute thermal equilibrium. Reaching that equilibrium is not an arbitrary process. The transfer of energy operates through three strictly defined physical mechanisms. Those mechanisms are conduction, convection, and radiation. Which mechanism dictates the transfer at any given moment depends entirely on the physical state of the medium, whether the energy is attempting to move through a solid, a fluid, or a total vacuum. To master these definitions and actively test your recall of the physics involved, you can use our 24/7 WhatsApp coach as you study. Understanding thermodynamics requires looking past the abstract concept of heat. It requires analyzing how energy navigates the physical constraints of different atomic structures and spaces. We begin with conduction. This is the primary method of thermal transfer, restricted almost entirely to solid materials. This animated diagram illustrates the baseline physical constraint of a solid. Its atoms are fixed in a rigid, repeating lattice structure. When a heat source is applied to the left side, those localized atoms gain kinetic energy, vibrating in place with increased amplitude. Because these atoms are locked closely together, their violent vibrations cause them to physically strike their immediate neighbors. The thermal energy is passed sequentially down the line through these continuous mechanical collisions. Relying solely on this lattice vibration is an inherently slow, inefficient process. This specific structural limitation is exactly why nonmetals, like wood or plastic, act as thermal insulators. Metals, however, achieve superior thermal conductivity through a distinct secondary mechanism. Look at this updated diagram showing the structure of a metal. We still have the fixed lattice, but it now consists of positive ions submerged in a sea of free, delocalized electrons. When heat is applied, these free electrons gain kinetic energy directly. Unlike the rigidly fixed ions, the electrons are highly mobile and rapidly migrate through the entire metal structure. As they shoot across the lattice, these high-energy electrons collide with distant ions and other electrons. This distributes the thermal energy almost instantaneously, compared to the slow, atom-to-atom mechanical collisions of the lattice alone. This also explains why fluids, liquids, and gases are incredibly poor conductors. Their particles are physically too far apart to sustain a continuous chain of mechanical collisions. Conduction is strictly a game of subatomic proximity. Without a tight atomic lattice or free-flowing electrons, this method of thermal transfer is effectively blocked. In fluids, the absence of a rigid lattice opens up a completely different pathway for energy transfer: macroscopic movement. This is convection. It is thermal transfer achieved not by passing energy between fixed atoms, but through the bulk physical movement of the fluid mass itself. This cross-section of a beaker sets up the standard physical model for convection. We have fluid particles suspended inside, with a localized heat source applied directly to the bottom center. The process begins microscopically. The fluid particles situated near the heat source gain kinetic energy and begin moving at higher velocities. Because these particles are moving faster, they push against each other more forcefully. As a result, the physical spacing between the heated particles increases. The volume of this heated region expands. Since the mass of the fluid in that region remains constant, this expansion causes the localized density to drop. Gravity dictates the next step. The surrounding cooler fluid has a higher density, causing it to sink downward. As the dense, cold fluid sinks to the bottom, it mechanically displaces the less dense, heated fluid, physically forcing the warm mass upwards. The newly heated fluid at the bottom will then expand and rise, while the fluid at the top cools, becomes denser, and sinks. This continuous, gravity-driven loop is called a convection current. Convection bypasses the slow atomic collisions of conduction. It physically transports the heated matter across the available space, driven entirely by differences in fluid density. But what happens when we remove the medium entirely? How does thermal energy transfer across a space with no lattice, no electrons, and no fluid? This diagram illustrates thermal radiation. The energy is carried by a single oscillating wave, representing the infrared region of the electromagnetic spectrum, traveling linearly across the void. Because radiation relies on electromagnetic propagation rather than particle collisions or fluid dynamics, it is the only thermal transfer mechanism capable of traversing a perfect vacuum. The baseline rule here is constant activity. All objects in the universe are continuously emitting and absorbing thermal radiation at the exact same time. An object only maintains a constant temperature when its rate of radiation emission perfectly matches its rate of absorption. These rates of emission and absorption are strictly governed by one primary variable, the physical texture and color of the object's surface. Look at this split-screen comparison of the two surface extremes. On the left, we have a dull, matte black surface. On the right, a shiny silver surface. Dull, matte black surfaces represent the maximum transfer rate. They act as the ultimate absorbers of incoming infrared radiation, and conversely, they are highly efficient emitters. Experimental evidence proves this. If you fill a matte black container and a white container with hot water, the black container will cool down measurably faster due to its rapid rate of emission. Shiny silver surfaces perform the exact opposite function. They are highly effective at reflecting infrared waves. By bouncing the radiation away, they become extremely poor absorbers and emitters. Radiation expands the parameters of thermal equilibrium, tying the rate of transfer directly to the interaction between electromagnetic waves and surface albedo. We can now apply these physical laws to an engineering challenge, designing a system that actively defeats conduction, convection, and radiation all at once. This 3D cross-section displays the standard vacuum flask. It serves as the ultimate applied physics solution for achieving nearly perfect thermal isolation. The architecture starts with its primary defensive layer, a vacuum gap between the inner and outer walls. This vacuum completely neutralizes conduction and convection. Without particles present, lattice vibrations instantly halt, and fluid density currents cannot exist across the void. The second layer of defense lies in material selection. The walls are glass, and the top is sealed with a plastic stopper. Both are insulators. Their atomic structures lack free electrons, which severely throttles secondary conduction, attempting to bypass the vacuum at the top. The final layer targets radiation. A shiny silvered coating is applied to the inner walls of the flask. As hot liquid attempts to radiate thermal energy outwards as infrared waves, this silver layer reflects the radiation directly back into the system, neutralizing emission loss. The success of the vacuum flask demonstrates that thermal isolation is a matter of weaponizing physical laws against energy flow, rather than simply increasing the volume of insulating material. To identify your weak areas in physics and generate a customized study plan for exam success, visit studybuddy.tech and take a free diagnostic test today.